First of all, thanks for showing up. Your presence is appreciated. So this presentation is obviously on sync architecture, and it's somewhat technical, but not too technical. So at any point during the presentation, please feel free to interrupt me if you need to adjust essentially the level if it's too technical or not technical enough, or if you have questions about the presentation, just go through. What I would like to present essentially is not only the nitty-gritty details of the particular our sync implementation, but really trying to extract some qualities from why we can sync together the way it is. All right, so the first, that's supposed to work. This is probably the most overused diagram of sync, because I put it in one presentation. There's not really much that you don't know already in there, so I'm not going to spend too much time. There is a traditional PDA to wireless generation diagram, and obviously Pocket PC is a slight variation of Windows Mobile, that these two boxes will be actually one. So what is a sync in our context? So a sync is, what we call async is actually kind of a misnomer, because what users experience when they sync is three very distinct protocols. So three very distinct functions that are put together each time a user presses the button to press sync. The three protocols, so there's actually a fourth one, which is just a directory protocol to essentially advertise these three services to the conduit. But these three things, sync station management, client application management, and client data management, each have obviously a different function. Sync station management aims at being able to manage the sync station, which means mostly at this stage clearing logs that pile up. So for instance, we clear the logs that are older, upgrading the version to a newer version if we have to, without the user doing anything or without us having to do anything pretty much. Or retrieving logs or PDs in case we need to do some forensics, or not PDs, but the actual sync station code. That's sync station management. Second protocol is client application management, also known as CAM. That is only provisioning, a PDA provisioning service. So we can essentially deploy our PDA applications to the PDA. And the last one, the client data management, is what we commonly refer as sync, although sync is much more than that, but that's really a user-centric synchronization. So while everyone who is using a given sync station will sort of fall under the same bucket as far as the sync station management server is concerned, while everyone who has, say, TPRI will fall under the same bucket as far as the client application management is concerned. The client data management server is going to synchronize data that are pertaining to a given user. So obviously, roster data, assessment data. So that's what we call. I guess that's what we call formally sync. So a sync is also a multi-message session. So for each of these protocols, SSM, CAM, CDM, there will be a session, and this session will be composed of many messages. And we will see in a few moments why this matters. One thing that is true pretty much throughout the entire sync framework is that we really want the server to drive the exchange. The reason for that is is really for us to be able to put as much smarts and intelligence in the server, which is a piece of code which we control much more easily, and really build dumb clients, or as dumb as possible. Because it's much harder to essentially maintain clients out there in the field. Even though we have a protocol to do that, it's still much more difficult to control. The last sort of quality the last quality of the sink that we have inside our generation is that the CDM, so the piece that exchanges the data, assessment data between the PDA and the server, this piece is transactional, and that means that it's built in to offer protection against interruptions. So when the company started, it was a much simpler scheme, and what we noticed fairly quickly is that additional there are things that happen out there that you cannot really avoid. So various interruptions, bugs in our software, and so on, which would leave essentially the sync server to wonder what happened because the async had stopped in the middle and then it was trying to reconcile, but it could not quite do that. So we had to actually manually fix problems. So that proved costly as traffic rose. It became more and more expensive to do that, which is why eventually we put the notion of a transaction in sync, which is really a mechanism that is designed to guarantee that all changes between the client and the server are either all applied or never applied. I mean, there are actually exceptions, but that's the gist of the idea. Any questions so far? Yes?
Although the server-driven exchange principle sort of underlies it, the client has to request
yes.
to start the session.
Yes. So the client will always initiate the dialogue, and one reason for that is just the way networks are built in general, and the way sort of protections around private networks are built. So the school will not allow anyone to initiate a connection into its network. It will only allow communications to flow back if the session was initiated from within the school. On our end, obviously, since we provide a service, we essentially drill holes in our firewall to let customers connect to our service. But you're right in that the theme is the client initiates the connection and then sort of responds to what the server decides. And so the decisions are really all implemented in the server, and the client side is very much an event-driven model where you can just react to what you're being given. Obviously, there is some amount of, I would say, innate behavior built in the client, but we try to keep that behavior to the minimum.
So what I was getting at, at no point in the future are we going to be sort of polling all the Windows CE devices in the schools to try to just grab any new data that appears. The model of them initiating the dialogue is pretty much the way we're going to do it.
Yes. So now, based on this diagram, I want to spend a bit of time on what I would call the core. So the core of sync, which is independent of any application, and then spend some time with the sync station. So the core of sync is really, it is the implementation or the incarnation of a fairly simple algorithm, which is its aim is essentially to bring the PDA and the server in sync or synchronized. To do that, if you want to, I mean, if you take pen and paper and you start to work out the various steps of what you need to implement this, you will find that so there are various strategies, some that are very robust but consume a lot of essentially not bandwidth, but require the client and the server to exchange a lot of data. And then there are other strategies that, on the other hand, will optimize the amount of information that's exchanged each time both client and server connect. But of course, if you exchange a lot less data at a time, that means you are building your strategy based on assumptions or on shared knowledge. And our goal is obviously to build an optimized version of Sync, because we realize that network resources in schools is not really the most abundant resource that they have. So we really wanted to be able to exchange the minimum while still guarantee some amount of reliability, but not send too much stuff if it's sort of known by the server, which in turn means that the server has to keep a representation of the PDA of each single user at each single sync point in time. So as it turns out, conceptually we have the history of all, we can track a PDA throughout its entire history, and each time it syncs, be able to tell. So this is what a PDA for user John Doe had on September 29, 2004, which has some, obviously some impact on the amount of storage that we need, because if you keep that server-based client representation in the server, then the question is, how do you keep it? What do you do as they accumulate? So while we're able to minimize the amount of information that's exchanged between the client and the server, the cost of that is that the server has to do a lot more work and maintain a lot more state. So the algorithm still remains very simple. It's essentially the server applies client updates, the server computes what the client should have, taking into account these, and then the client then applies server updates. But the ordering matters here because it serves as a sort of simple conflict resolution policy between the client and the server. I mean, there are different models of synchronization where you can have essentially some form of arbitrage between updates, conflicting updates. In our case, by design, we say, well, the server is pretty much always right, and it's going to prevail. That doesn't mean that we don't give the client a chance to send whatever it has to send. And we're actually very conservative about that. That is to say that we'll really do our best to apply any changes that originate from the client, so presumably assessments. And if we're not able to, we won't discard these changes, we will just request the client to send them again next time at the next sync. The idea behind that decision is we hope that maybe it's something that we need to fix internally, some data are not properly aligned with the database, and by the time the next sync will happen from that customer, we will have been able to resolve the issue, and the client updates will be able to be applied by the server properly. So that's really the core. In the core, this algorithm is independent of the application. So Dibbles, TPRI, PALs, anything, that they all follow exactly the same logic.
So you keep an image of the PDA on every sync, or do you apply a diff between syncs?
Yeah, so we do. The question is whether we. So since we have a client-based representation and we keep that throughout the entire history of the POM, the question is whether we store, let's say, the first, we create a representation and then only store what's changed between each sync, or whether we store the entire thing each time. The answer is we store the entire thing each time. I mean, there are some optimizations. If there are no changes, we don't create a new image, but otherwise we will, because otherwise if we only store, let's say, the representation of the PDA at the first thing, and then store just simple changes, when you want to essentially rebuild, or when you want to invoke in the server what the PDA was, the state of the PDA, the last thing, you have to go back to the first thing and then sort of successively apply all tiny changes, and that will give you the current state.
So in a sense, it's
It's
storage versus processor power trade-off.
Yeah, yeah.
And storage is a resource we have.
Yes, so
It's also a complexity trade-off, because even if you did it the way CVS does, where you store the latest and you use dips to find it first. Since this code is written in PL SQL, which is not the easiest thing to maintain, it was just way simpler to actually store the complete image.
okay, so I mean that's a few words what I have to say about the core. The sync station on itself, I mean, rather than going over individual bits which might not be terribly relevant in the context of the discussion, I'd only say that we actually have 3 different flavors of the sync station. The first one is our commercially supported one, so the one we offer customers. It's based on HotSync, provided by Paul. It's just a mix of C++ and Python, so it runs essentially embedded Python. When customers press sync, they actually use Python, so Python is just a scripting language. The second flavor is something that we've built with the hope of possibly deploying it to schools. It didn't quite happen that way, but it's a sort of Mac-based or Linux-based prototype that's much more powerful, much faster, has more capabilities, and it is actually used by deployment now. So if you go this route, so if you're a customer, you can sync at most 1 PDA on a sync station at any given time. If you go this route, you can sync up to, well, actually there's no hard limit, but usually you can sync between 5 and 8 on a reasonably decent machine. Just a mix of, it's pretty much the same Objective-C for the Mac. The Windows Mobile Pilot, which is going to start in a week, is a C# code base. Why did it change? Well, the level of support of Python back then is on Windows Mobile. It was not great. I mean, I don't know if it's changed now with Python and things like that, but we decided it would be safer to go with the Microsoft-supported language of the platform rather than go how we can go for our own path, and I think that's a bit off.
Yeah, it's working great.
And is it active sync based?
Yes, I forgot to mention. Yes, it is active sync based.
Or like with Vista, it's going to be
Windows Mobile
whatever.
Device Center or something.
So we are building on top of whatever the way it is that the C device exchange with the desktop. Right?
Well, no, not really, because the difference is that whereas with HotSync, sync is built into this model of the conduit between the desktop and the pilot, and the Palm Pilot. With Windows Mobile, all the logic is on the device itself. All it's using ActiveSync for is a connection to the internet.
Oh,
But the device itself is saying these are my changes and connecting the servers.
so there's no, is there a conflict then?
There's no conduit.
So is there any software that has to be installed on the computer?
Except for Microsoft ActiveSync, no, there's no wireless generation software on the computer.
That's right.
You could run directly off the device.
And right, if you
So if you have Wi-Fi, you can just sync right from the
So
device. You don't need it.
we might be wireless.
We might be truly wireless.
We might live up to our name at some point.
Any questions on the station? I mean, yeah, if you want, I can delve into details of how it's built. It's something that, I would say it's something that hasn't changed significantly in about a year or two. So it's basically very stable. We fixed a few bugs, but that's about it. So now that I have described essentially the landscape, I would like to address one particular aspect, which is scale, which is I think one key aspect that drives all the architecture decisions, or it's a key driver in the architecture decisions. So we just broke our 30,000 steps a day record. It was about a week ago. So 30,000 sinks a day, that means roughly 200,000 HTTP round trips per day. They are HTTP because we actually use HTTP to send data between the school and the server. That's the channel that we use. It's a well-known and well-supported protocol, so we just for free there. So 200, HTTP request response per day. That's not a lot in the context of your traditional web server, MySQL, PHP, Apache-based web server. In our case, obviously, we do a lot more processing than the usual PHP website. So, which means that we need some fairly serious hardware to be able to address that. In terms of so these 30,000 sinks per day are obviously not spread fully over the entire 24 hours. It's mostly between 10:30 to noon and then 2:30 to 4 p.m. And we, roughly have one sink per second at that time running through the system. And each sink will take around 80-90 seconds to complete. So we constantly have a bunch of concurrent sinks executing, and every second of each one is finishing on average.
Are those HTTPS?
Yes, yes, and I will show you what it looks like from a physical standpoint. So in terms of growth, and that is the number of sinks per year, that's per calendar year. I didn't split by school year, but that gives you an idea of this is, 4 or 5 or 6 or 7 estimated. So it's growing nicely. It's somewhat linear so far. So we're getting more and more traffic, and also, well, I guess that's the number of sinks at the busiest day in any year. Number of sinks we had that day. So this year, actually, so far, I was surprised that we go that far, because even last September we had thought that number of customers growing less exponentially than the years before. We'd have fewer sinks than we actually had, so it was quite surprising. And I don't think that in 2007, well, depending, we might break this 30,000 record again. January in the company industry is traditionally the busiest day of in terms of peak. We get the peak in January. Well, one of the reasons used to be that I guess TPRI, kindergarten, doesn't have a beginning of the year assessment. I don't know if that's the sole driver anymore for having so much traffic.
Now,
Right, so that's not true. It used to be. So I guess also everyone, while in August or the school years has some, not all schools start exactly the same day in January. There's not much. There's not a lot of leeway in when they can start. So let's take a look at what, from a physical standpoint, we put in place to support this scale. So the physical view is this traditional firewalls, load balancers. While there's only one of each represented, they're actually double for redundancy reasons. 3 machines or 4, depending, Linux machines, called sync dogs. So all the production machines are called dogs. They're dogs of some sort. Sync dogs, data dog, NFS dog, wing dog. But so we have 3 sync dogs. This is our data dog, which I call the transactional database.
I like to refer it to. I like to refer it as the transactional database.
Yeah.
You're crazy.
So that transactional database, as I don't know what to call it, essentially it holds up all our data. So that's the master. This is the guy that we watch really closely, because not only is it the key, there's only there's only one active at any given time. And also, if that guy disappears, obviously the wealth of data that we have can so far only be in jeopardy. Backups and so on notwithstanding, but that's really crucial. So in terms of, so this guy has its own storage, SAN is storage and area network, so it's just a gigantic pile of hard drive that can house all our data. So these three sync dogs actually need to talk to three different machines. So obviously they need to talk to the transactional database because they, so a PDA connects to the server, and the server will need to fetch from the database the representation of what the PDA has to be able to apply, change it, and so on. So obviously it has to go to the transactional database. It has also to go to the transactional database to be able to ask, so what's up to date? Should I send anything back to the client? So that's for this guy. That guy they use, they connect to it also to share state. So let me just explain why this is the case. As I mentioned, we had about 200,000 HTTP round trips per day. What that means, and I also mentioned at the beginning of the presentation, that each session is a multi-message exchange. So that means that each session will be composed of a few round trips. And that's pretty much also the case for the web. Now, in the traditional web application, what you do is you have a long-lived server that will essentially serve requests. So it will keep the state associated to a session, such as what has happened so far and so on, internally, and not save it somewhere or something. In our case, because we don't want to have, it's a decision that we do not want to have a long-lived server. Because once you have a long-lived server, what if its state starts to degrade? What if when the session is finished, the cleanup is not cleaning up properly after itself? We decided to have one small process come to existence each time there's a PDA connecting. So the PDA can connect as part of the first message of the session, say hi, I'm PDA, or it can reconnect while it's doing so inside of the session. So let's say a session is going to be 5 messages, or not 5 messages, 5 round trips. So if the PDA is at round trip number 3, then obviously it will connect to the sync dog, and the small process will just appear and take into account, so start serving the PDA request. And now there are a few things that we'll need from the previous invocation. So round trip number 3, round trip number 2, round trip number 1, things such as the message number and so on. So because we need to sum up, because we want to not have long-lived servers, and because one session is many messages, each time there's a message that comes in, the short-lived server has to find somewhere whatever context is associated with that session. And that somewhere is this. Is that clear, or is
maybe another detail to add to this is that when the PDA connects to a server, it might not be the same server as it exchanged the last pair of messages.
Right, that was what I was about to ask. So you don't use the same sync dog for an entire duration of what we consider one sync.
Exactly.
Yeah.
So the sync dogs stored their session state on an NFS server,
So
which
they
they
can
share.
find, yeah, so
Yeah, yeah.
they can all, it doesn't matter which one gets hit, they can find.
Exactly.
if you look at the web applications, the story is different, and in particular the state here is, well, so there is the guarantee that if you start a session, if you open a web app, it will always hit throughout the duration of the session the same app docs.
Right.
Correct, unless you time out to an activity. But that like 20-minute timeout is what we would call a long-lived service session, right? Is that
Yeah. So while a process on a sync server running on a sync dog will last for 30 seconds and then die, and then another one comes in. So we always have, because we have more than one sync going through the system at each time, we'll have however many sync servers running and dying and so on. And that's fairly stable. That's the good thing is it's so that the state doesn't degrade. The technology it's based on is the old CGI interface from 1996. So that's a very simple model, and that makes it more resilient than the web application servers that you have to load and that will run on the server for days and days on end.
What about encryption? Is that HTTPS?
So yes, well, yes, it is. Yes, although we do not mandate HTTPS. Actually, most, contrary to the web, most most syncs here use HTTPS. Actually, the vast majority. And the HTTPS is terminated at the load balancer level, which means that it's actually unencrypted traffic that flows between this point and that point.
So if they're doing like 5 round trips, does each round trip negotiate a new HTTPS session?
Yeah. Yes.
They do.
Absolutely. Questions? Okay. So, with this in mind, there are 2 types of strategies to scale that we have to actually adopt at the same time. The first one is to scale out, and that only applies to SymDocs. So you've seen, let me show you again. Essentially, these are hosts for processes to run and die. And this is where we store state, or this is where we store context and data that will outlive the duration of this server. So, by that, hence, we can only parallelize sort of this layer. So we need more processing power of a certain type we can add traditional SymDocs. But since they all refer to they must find a place, a physical or a logical location where they can exchange data between each other. We cannot quite adopt the same strategy for this guy or that guy. So scaling out, that means mostly, that's what applies to SymDocs. We have, as I mentioned, we use the old CGI model, which is one process per round trip or per incoming message. And the key there is you want to limit shared state between processes. So we use this NFS dog thingy to do that, but we keep that to a minimum. For the data dog, it's different. So for the transactional database, it's a different story. So far, our strategy has been to essentially write the x86 cheap machines wave. So as traffic grows, our demand for raw power grows as well, and we are able to get that for fairly cheap buying the Intel or AMD processes. But we still keep everything inside one machine, so each year we buy a bigger machine. Which means that at some point fairly soon we'll run out of machines to buy. Just that at some point there's a disconnect, or not a disconnect, but it's not growing the same. The price you pay for the initial marginal cost of the power goes up tremendously. So we are now running on it's a 16 core machine, which we hope to bump up to 32 maximum when you have higher, sort of more dense processes. That's going to be probably it. Then the machine is expensive. The software to run it becomes is expensive. So everything starts to become more difficult.
How much does the current database server cost?
It's about, so the bare bones is 50K, to which you can add maybe another 50K of memory. that's without any drive. So while in the newer, in Jillian's desktop, laptop, there are 2 processors. You can imagine that we have 16 and maybe 32, but at some point it becomes a problem. So we have to go to partitioning. So partitioning meaning we have to start slicing our data into our data space we have to partition it and actually run a partition on different machines, which will have a nice consequence of being able to buy smaller machines to serve small partitions. So now, at that point, we will be able to scale out. So suppose we add another, we start doing Europe, for instance, or then we could have a server dedicated to Europe, or a country in Europe, or Asia, or anything, as opposed to have everyone in the same huge machine. There's another good thing about partitioning is when there are problems, do occur. If a database has problems, then maybe you would shut down services for only a subset of our users as opposed to all our users the way we do it now.
I don't know if this is the same question, another database question, but why not always just have a separate database for each district? Or I don't know the business logic well enough, but why was the decision made to put all the data into one database in the first place?
So I could, the actual why. So my interpretation would be twofold. The first thing is, as you start as a small company, so there's some overhead in building, in architecting for a partition space. So you want to go fast and customers, or you don't really want to spend cycle building things that you don't really know whether the company will reach a stage where it will be able to use the partition model. Now, obviously, we have to, but a couple of years ago, it wasn't that clear. And so that's the first thing. The second thing is, at some point, we still do need a unified space where all the data live, because if you want to extract reports and things like that, if you want to gather data that span across partitions, say partitions are states, then if you want to compare two states or get an idea for all our customers.
How is it being partitioned?
It's not completely decided yet, but there are a few dimensions that make sense. So state is a strong dimension, sometimes because particular regulations will prevent data from the same state. So that's really the...
We've been asked to aggregate up to the state level and never higher than that. So it's say peers right now that treat each state as separable. And
we can do it by user, but then still we have to group them in a way that they have to be simplified district. So state is groups of state actually. So we don't want to have 50 databases. We want to have 2 or 3, and they'll be either we distribute the big states, the large accounts on, say New York on one, Chicago on the other, Texas or Miami on the third, or or buy big machine for these guys and then smaller machines for the less active customers. Right, let me move on to a few challenges that we have faced and what we are facing. The first one is data storage. So it goes back to what you were saying so there's this trade-off between storing everything at each sync or storing just individual image and then just tiny increments. So as we stand, so we use blobs, and blobs is just binary large object. It's a data type in Oracle that lets you store essentially arbitrary data. You don't really type it in, so it's not like a string or a number or anything, just anything. And that's how we store the server representation of a PDA. We store it in a blob. We have about half a terabyte, roughly a bit less than half a terabyte of blobs online, so that in the database. These blobs have some unfortunate properties in terms of their management. So we generate about 100 gigs per month of these logs, and we have been forced to take, so each assessment window, we actually have to clean up the database. So we take some of these logs and move them outside of the database. They are still available on demand, but they are not inside the database anymore. So that way, we can keep the envelope or the storage fairly constant. So we can say we will not use more than half a terabyte of data at any given time. Because the maintenance is by nature a risky operation, we will lift these limits. So there is a project currently to increase the amount of storage significantly to not have to be able to keep more than 0.3 or 0.5 terabytes online in the database, which if you compute that gives you about an assessment window, and that's it, and we have 3 per year. So ideally we want to keep one assessment window, 1 year in the server completely, in Oracle, in the transactional database, and just do a major cleanup at rollover, because that's really a period of time when it makes sense and the impact is much more limited than right in front of the window, or shortly before the window, or shortly after the window, which in the current setup is we always have to do maintenance. It's either shortly before, in the middle, or shortly after, but we don't really have the luxury to do that much longer. So what it is, essentially, I mean, it's a generational garbage collector. That's what it is, and it's really difficult to manage because it's a lot of data. So it's one thing so I would say it's a lot of data. So each operation takes upwards of a couple of hours at least. So which means maintenance is only weekends at night. So it's not something that we could run every day or something like that easily. So I mean, we're trying to address that. But
is it fair to say that the log storage difficulties, like the fact that the Oracle database can't reuse storage after you delete the log, that these are Oracle bugs?
Yeah.
That like half of the system is a workaround for Oracle bugs.
Still, I think so. Yes, that compounds. It compounds the problem that it is difficult. So you have all your logs, and it's not actually that easy to identify which are still relevant and which are not. So there's not a clear partitioning. You can't just say, well, everything from last month is not relevant anymore, because there are actually cases where data from last month are relevant to your thing happening today. What we show is data from last year, last school year, they're not relevant anymore. So yes, in a sense, so Oracle really does not make our lives any simpler, but I think there's some intrinsic complexity that we have to overcome. So performance is obviously another challenge. The estimated impact of sync on the available power of the transactional database is 60%. So note that I don't mention the impact on the sync dogs, because the front end is essentially the sync dog, because we can just add one and that's it. We just grow our available throughput. For the database, because we so far only have one database that's a critical factor. So during the day, 60% is sync, 40% is web, roughly. Performance also introduces, the way we've built the system introduces some interesting effects between the front end and the back end. So we are, in warehouse generation, we always run with a minimum margin we're close to the limit for pretty much all around. I guess. So we found ourselves in situations where, for instance, it's a busy day, so you have your front end hammered by the number of things coming in, and the database is doing fine. Then you say, all right, that's easy. Just going to add another front end, and we'll see, that problem will be solved. So you add another front end now, so the front end can send more things to the database, but now the database starts becoming the bottleneck. So things pile up in the front end while the back end, so the international database, is processing them as fast as it can. And there's I mean, you can see when you grow the front end pool of servers, you can see sort of traffic hitting the database, and the database load goes up, and then somewhat stabilizes. So each time on this system, because of the way the sinks are built, they are multi-message and so on. They require many exchanges. When you make a modification, it's sort of very difficult to predict exactly what's going to happen. And so far, each sink, on average, spends roughly 8 seconds in the database. So it takes 8 seconds to compute everything.
Which is considered a lot, right? If one of our web pages took that long to, so you bring back a student list, it would be considered a real performance problem. Right?
Yes, absolutely.
Yeah.
So in this case, it's doing more. I mean, while the web page is essentially it's calling the database logic to get the data for, say, one class, one type of report, one application. Same has to do it for a given user for every single application. So it's a lot more intensive, and it's not quite spending 8 seconds right there, sort of in one chunk. It's a bit. I mean, there's a big chunk that's computing what's up to date, but there's some amount of time spent sort of spent before that time. So in each message, there's a bit of time spent there. And it's not actually doesn't feel that bad because the average duration that we can measure from the user perspective is around 80 to 100 seconds. So the database, in the grand scheme of things, is not spending a lot of time in the database. If we have that duration, we would gain much from the user's perspective. We would feel about the same.
But we would be able to serve twice as many sinks.
Yeah. True. Third out of 4 challenges that I picked, the SingStation upgrades. That proved crucial because it's really where the sort of changes are much more difficult to apply. So you have many options. You can say, hey, we have a new version of SingStation, please upgrade. Put that on the website, and you have maybe 3% of people upgrading. You can send a CD to every single user, so that's fine, but it's going to cost a fair amount of money. Or you do the Windows update type of thing where you ask the user to connect and to click a button to update. The last thing which we decided to do is to have it done all automatically. And that's really part of the service offering. So initially when we built it, we had still manual safety. So we have to have an operator actually say this SingStation needs an upgrade. But in the end, it proved just too much work to even have someone even building tools to allow for that. There's just too much stuff. So now it's really each time the SingStation connects, it asks the server, or actually it says to the server, this is my version, and the server says, hey, there's a new version, or oh, you're up to date, so carry on. So the automation is really what was a big challenge and what was being off? What is it being off? The last thing is operations, and the message there is simple. It is that it's really worth building tools. I mean, there's no way around that. Because you're saving a lot more time building tools than you think you would be. This pretty much concludes my my presentation, but I would just add one more thing, which is what's coming next, in terms of sync. So far we've been able to cope with growth by adding more servers in the front end or replacing the backend server with a bigger beast, while maintaining the same code for almost a year now. I mean, you could trace the current code back to 2003 or so. It has had a major overhaul in summer 2004 for transaction, and then another overhaul for SingStation management in 2006. But we try to keep everything changes fairly minimal, so change sets, and limit the number of rewrites or that kind of stuff. Even though the code might not be the most beautiful code or best best design award type of code, but it works. So we want to keep it stable for a while. Though there will be 2 major upgrades this year. Definitely one this year, the second one starting this year, but I think carrying over to the next year. Port to Revel 10G. So that is a disruptive change, even though the code itself might remain fairly identical. This will raise the big question of it's an entirely new environment, so we must make sure that we can deliver the same amount of performance and the same amount of everything, pretty much, as our current 9i database, or Oracle 9i versus Oracle 10G. And the second one is the logical partitioning. So I'm sure you're all aware of this project, which is to partition everything slice by say state. And that will affect every single system in the company, at least on the technical side. And so sync will be like that. Thank you.
Thank you.
Question.
Yeah.
Do you think that doing performance
day in, day out in our local schools that are some of them artifacts going way back, but a lot of them artifacts of sort of recent history in the school system's efforts to change around the assignment and assessment in particular, are standards which have kind of arisen with a dual meaning where the two meanings don't have, are often, I think, at odds with respect to the potential corrections that you talked about. One being the standard in the sense of a measure or level of quality that the system should be yielding for children's individual experience and across the system. And then the other, this sense of a convention or commonality across the experience of the kids. And standards have become, I think, more and more important in a way that has sort of surprised me in the last few years, rather than less and less so. And by that I mean standards in the latter sense of performance. And so I'm curious what your thoughts are about where that's going and how, what can alter that. And then sort of related to that is the dynamic between assessment and accountability, where assessment inherently isn't itself necessarily about the accountability of the system to various other stakeholders, but most of the innovation in assessment in our industry right now is being driven by the accountability movement, which I think tends to cut against a lot of the direct innovations that you're talking about. So love to hear your reaction to all that. And just lastly, if the basic assignment in higher ed were to, in the quite near future, become, as you said, not the research paper, but a kind of participation in the creation of the whole, whether stewardship or part of the Wikipedia or something else, what does that mean for the assignment in K-12?
Accountability, I think, is one of those things that's going to be under a huge amount of pressure. That the justification of the sequential educational system is in various utilitarian extrinsic consequences. And the driving force behind a lot of what seems to be emergent in our culture, I think, is committed to, strangely enough, participation in things that people judge worthwhile, not primarily for their consequences, but because they enjoy them.